We want to cover now a concept called conclusion error, and this is the primary reason why we can never use language in our research such as research proves. At least within the social sciences, there is always a possibility that we are wrong. And hopefully this sort of makes intuitive sense to you since we're talking probabilities. Since everything is a probability, there is still some probability that we're wrong. Anytime we get a result, there's still, regardless of how small of a probability, it's still a probability that we're wrong. Typically, the way we sort of graph this out or chart this out is in this little matrix here. And you'll notice across the top it says the null is true and the null is false. Basically, what we're saying here with the null is true, if you recall, is the idea that there is no difference. Okay, there's no effect going on. With the null is false, it's the idea that, hey, that there is some effect here. The null is wrong. Okay, it's not the hypothesis we're going to accept. On the left-hand column, you'll see reject the null and fail to reject the null. Reject the null is basically the idea that a value falls in this rejection region that we've talked about. When we say fail to reject the null, it's basically just this weird way, funky way of saying that we had a value that fell somewhere in here. It was not in the rejection region, so we cannot reject the null. We fail to reject the null. In other words, there's no effect. We're stuck with basically having to live with the null hypothesis. Scores are roughly equal. So if we go back to our last example looking at long-term alcoholics, if we reject the null, basically what we're saying is the score fell out here. There was a difference with long-term alcoholics IQ versus the population of non-alcoholics. If, however, their value had fallen in here somewhere, we would have failed to reject the null and said, listen, that 98 really wasn't any different than the 100. We're not going to reject the null. It's probably just roughly equal, at least not so much so that we would say it's statistically significant. Probably just a sampling variability issue and not something related to alcoholism. Okay, so now if you'll look at the top left quadrant of that matrix, you see the phrase type 1, okay, and then the little alpha. Basically, type 1 error is defined as this. It's rejecting the null when we shouldn't have, okay? Or we could say it this way, rejecting the null when the null was in fact true, okay? In other words, we got a score out here. Let's use our alcoholics example again. We found that alcoholics had a significantly lower IQ, but it turns out it was just a funky sample, and really alcoholics don't have any different IQ. Just was something to do with our sample. And if you think about this, the little alpha there in parentheses is how often we are likely to commit a type 1 error. So we go back to our alcoholics example. We found that our P observed in the last example was 0.04, which I told you if I took enough samples from the normal population, 4% of the time I am going to get an IQ average of 98. So if I get a score of 98, what's the probability that I am wrong about my rejecting the null? In the long run, 4% of the time I'm going to get that score. So what we would say is that my type 1 error rate is equal to this 4% because 4% of the time I'm going to get this value. Now, where we have to be careful in our language is that if we were to say, yeah, the odds of me being wrong or the odds that my study is wrong is 4%, is not true because remember, we don't know on a single study or a single case. All we know is in the long run. In the long run, I'm going to get a value of 98 4% of the time. Has nothing to do with alcoholism. I'm going to get a 98 4% of the time. But because that isn't likely to happen, when I did get the 98 for alcoholics, I conclude, it's probably alcoholics, not the sample. So I'm going to say that long-term alcoholics have a lower IQ. But again, I could be wrong. So in our research, we'll never say research has proven anything because I've just shown you we are always at, or at least have a probability of being wrong. So that's type 1 error. I reject the null when I shouldn't have. There is an associated type 3 error. It's sort of related. There's not a real clear place to put this, but type 3 error is basically I reject the null, but it was in the wrong direction. So with the alcoholics, we said they had a lower IQ, but let's say it turns out all the other samples I take of alcoholics, they end up having a higher IQ. That would have been a type 3 error. I correctly rejected the null, but it was in the wrong direction. Okay, so that is a type 3 error. If you go to the lower right-hand quadrant, we have what's called a type 2 error. And then the notation for that is that capital beta there. Basically, it's this idea that I failed to reject the null when it turns out that the null was wrong. Okay, that's horrible ways of wording this and very confusing ways. I don't know why we as statisticians can't make this a little more simple. Maybe it's we like to confuse people. But when we say fail to reject the null, what we're saying is I've gotten a score somewhere in here. It was not in the rejection region. So I can't say the null is wrong and then pick my hypothesis. I'm stuck with the null. But in a case of a type 2 error, I find a value out here, but it turns out there really are differences between alcoholics and non-alcoholics, or whatever it may be that I'm studying. My sample didn't show it for whatever reason, but in reality, there is a difference. So that's a type 2 error. I failed to reject the null when I should have. Type 1 error, I rejected the null when I shouldn't have. Type 2, I failed to reject the null when I should have rejected it. Hopefully that makes sense. We'll talk about it more and more. Just kind of get this in your vocabulary. Hopefully you understand it because you'll hear a lot about type 1, type 2 errors as you read research. Okay, a couple other things I want you to know is that type 1 error can be increased. Okay, it can go beyond sort of our alpha here at this point. And there are 3 reasons that I want you to be familiar with. One, if I run multiple tests on the same data, I can increase my type 1 error. So every test I run has 0.05. If I run multiple tests, that 0.05 sort of compounds, and there is a formula we'll look at later in the face-to-face section. But just be aware, if I run multiple tests on the same data, I'm increasing the likelihood that I'm finding something that's just sort of accidental, if you will. The other way we can increase our type 1 error is if I start off with my analysis looking at my two-tailed test, and then after the analysis I decide, I want to look at a one-tailed test. Not okay, because you are increasing the likelihood that you're going to be able to say you found something when in reality it wasn't anything but just a wonky sample. All right, the third way that we tend to increase our type 1 error rate is by violating assumptions of our tests. And this is potentially a big one because we don't always test the assumptions of our analyses. The end result is we may be finding a lot of things that we say are significant when it turns out they really aren't significant. And this is through violation of assumptions. And we'll talk about this more when you get here in face-to-face. We can also then, if we can increase type 1 error, there is a way that we can sort of adjust for what we call as our type 1 error inflation. And things that we should be doing, and again, we'll talk about this more as we get into other tests, but there are ways to legitimately decrease then this error that might be increased from some of these other things. And probably the simplest way that we do this is by just simply adjusting our alpha. We can make this smaller and smaller so that it becomes harder and harder to find that probability, which then makes it less likely we are committing a type 1 error. So if we decrease or adjust our alpha, we're going to also decrease our type 1 error. On the other hand, we can also decrease our type 2 error. And this is, I would say, beneficial. So if we think about what a type 2 error means, it means that we say there's no significance when in actuality there is. Now, for us as researchers, we would like to be able to reduce type 2 error. We want to be able to find an effect if there is one, okay? And the easiest way to decrease type 2 error is by increasing this thing we call power. And power, statistically, is defined as 1 minus beta, or 1 minus type 2 error. If type 2 error is a certain value, then power basically is what's remaining from that. The definition, the verbal definition of power, is basically the probability of finding an effect if in fact there is one. So whenever we use the term power and talk about this idea of power, it's really how likely am I to be able to find an effect if in fact there is one out there. And sort of the gold standard for social science research is we typically don't want to conduct any research unless we at least have a power of 0.8. Or another way to word this is unless we're 80% likely or have a probability of 80% of finding an effect if it is there. And the easiest way to increase our power is simply to increase our sample size. So if, as we start looking, let's say at your dissertation, and you come to myself or Dr. Gollery or Dr. LeBlanc, and we're looking at your study, and we're saying, hey, yeah, you're kind of flirting with not having enough power. Basically, what we're going to try to tell you to do is, if at all possible, collect more participants, because that inherently increases power and increases the likelihood of being able to find something if there is, in fact, an effect out there. And so that's what I want you to understand about conclusion error. Again, we'll talk about this some more as you come for the face-to-face.